Okay, so yeah, good evening. My name is Mohammad and today I'll be taking the ninth live session for the course Chemical Process Intensification. And this week, the the course content was extensively discussed on the process intensification performed on the unit operation distillation. So yeah, so if you have any doubt, you can feel free to chip in, ask. Otherwise, I will continue to discuss what has been discussed briefly in this week. So, yeah. So, 1 second. Yeah. So, one of the common example that comes whenever we talk about process intensification, especially in regards to the distillation, is the process intensification via reactive distillation. So in previous modules also we have discussed that process intensification can be one of the ways to achieve process intensification is to combine two or more unit operations successfully. So one such combination is reactive distillation, which is very common, and it is one of the very successful stories of the process intensification technology. So what happens is you combine the reactor unit operation where you are performing reaction, and you are also simultaneously performing distillation as the separation task. So you are combining both of the reaction and distillation together as a reactive distillation operation. So it has been it has been developed since the early 1920s. So it has a very long history, and still people are looking towards it, and yeah, it is a very successful story. And so it is developed since early 1920s that made a strong positive impact in the chemical process industry. And so imagine a success story that is still relevant to date and that has been developed in the 1920s. So it is one of them. So every subject has its own major milestone which is still regarded as important. For physics it might be relativity, and so but for chemical engineering it was one of the important milestone in the process intensification area that it was the reactive distillation was developed. So the most industrial scale reactive distillations presently more than about 150. So there are various versions of it, and so that are operated worldwide today are at capacities of more than 100 to 3000 kilotons per year. So as per the Hammerson in 2007, and that was started about more than 30 years ago. So yeah, the technology still holds to this day and it is still relevant today. So that was one of the such significant boost that nobody, no such process intensification or innovation has yet to come par into this. They can beat reactive distillation. So on an overview, so the reactive distillation allows reaction and separation to take place simultaneously inside the column. That is, we have discussed that okay, you are basically combining the reaction unit operation and the separation unit operation task to combine both of them to get a reactive distillation column. So it combines both of them. So it basically thus providing a valuable synergistic effect that overcomes the equilibrium limitations of many reactions. For example, like transesterification reaction, etherification reaction, hydrolysis, dealkylation, dehydrogenation, condensation, and isomerization. So the reactive distillation is not only just used for the slow reactions where the reactions will first happen slowly, then in a controlled manner you will perform distillation. So it is not such the case. One thing that comes to the mind is that you might intuitively think that if you are trying to combine two such processes, then it might be very specific for slow reactions, but no, it is also used for fast reaction. And there are quite few limitations we will discuss, but yeah, so the reaction distillation is also used for fast reactions. Also used for fast reactions, and the concentration of one of the products or the reactants may lead to the undesired side reaction. So usually such fast reactions also have one of the side reactions or coming from the product. So basically you need to control that also. So how to control it? It is to control such a scenario where one of the products or reactants may lead to undesired reaction. So one of the way is that you will reduce their concentration in the reacting phase to the minimal levels to hinder the undesired reaction. So basically to check out the undesired side reaction, so what you will do is you will limit or you will control the limit on the concentration of that reactant of the product, whichever is the one causing that side reaction. So you need to control that. So basically reduce their concentration. The reactive distillation system comprises of homogeneous and heterogeneous catalyzed irreversible and reversible reactions covering large range of reactions. So reactive distillation system, basically they also come in homogeneous and they also come in heterogeneous catalyzed systems, and those are also a major lot of them are irreversible, and they are also for the reversible reactions, so covering a very large range of reactions. So they are quite versatile. So whatever you pick up any reaction, most probably there will be a reactive distillation setup for it. So the reactive distillation is also called as catalytic distillation. So another name for the reactive distillation is the catalytic distillation. So you get it. Basically, the reaction generally requires catalyst. So and you are also simultaneously performing that distillation. So why not, instead of calling it reactive distillation, you can also call it as catalytic distillation. And the reaction in reactive distillation considered include heterogeneous catalysis reaction, homogeneous catalysis reaction, and thermal, which is non-catalyst because it is thermal. So you directly provide whatever the heat energy is required to cross the energy barrier. So such reactions also reactive distillation can handle. So in nearly all cases, reactions take place in the liquid phase, but the reactions taking in place in the gas phase and locate the catalyst in the vapor phase of the column is conceivable. The separation by the use of vapor-liquid composition difference. So generally, in most of the cases, reactions will take place in the liquid phase, but for some reactions, for some scenarios, for some systems, reactions will take place in the gas phase, and the catalyst will have to be basically dispersed in the vapor phase of the column. So in such scenario, you need to employ the separation by use of the vapor liquid composition difference. So that is one of the way to do it. But other than that, so in the reactive distillation, you can also handle heterogeneous catalysis reaction, you can also handle homogeneous catalysis reaction, and you can also non-catalyst thermal reactions. So yeah, quite a wide variety, and we will discuss on various other special process intensification that has been applied to the reactive distillation to basically give birth to new types of reactive distillation setups. So we will individually discuss them in detail. So socio-economic environment point of view. So what is the importance in terms of socio-economic importance that the reactor distillation should be developed. So the importance basically comes from the 3P intensification point of view that we have discussed in initial weeks about 3P scenario, where people, planet and prosperity, all three of them, the synergy between all three of them is required to perform the process intensification in the right direction. So what are those 3Ps? Those 3Ps are basically people, planet and prosperity. So the prosperity aspect of the 3P scheme looks upon the economical intensification that will take an advantage in the economical area, and where the your target variables are variable cost, capital expenditure and energy requirement reduction. So in all in cases, these are reduced by 20% of or more when compared to the classic setup of a reactor followed by distillation. So in a classic conventional system setup where you are performing distillation after the reaction, so those are both two different unit processes, not one reactor distillation setup. So as compared to such conventional classic setup, usually it is about 20% more economical. So yeah, why not? Even 1% is a lot of money. So just employ reactive distillation system instead of your conventional classic reactor and followed by distillation setup. So now in terms of environment, where it comes from the 3P, so the 3 in the 3P, it is people, planet and prosperity. So we have discussed about prosperity. Now in terms of planet, so planet looks towards the application of process intensification for the benefit of environment. So the important variables is basically the goal is to lower the emissions to the environment. And in all cases, carbon dioxide and diffusion emissions are reduced for the case of reactive distillation. So as compared to your conventional classic setup, where you are performing distillation after the reaction in a different unit operation, so basically in such scenario, your carbon dioxide emission is quite high, but as compared to your reactive distillation setup, wherein the carbon dioxide diffusive emissions will be reduced drastically. So now comes to the major point, or the major crux of the three triangle 3P setup, which is the people, planet and prosperity. So the not I would say that it is the most important, but they are quite equally important, all three of them. But coming to the people's benefit, where you are performing process intensification for the benefit of the people. Now who are those people? So and how you can employ. So in the triple P advantage, the point of people comes in terms of the process intensification for the social benefit, and where your variables of interest are the improvement on safety and improvement of health and society impact are obtained by the lower reactive content. So and they are also done by lowering the runaway sensitivity and lower space occupation of the your setup. So basically, if you compare the reactive distillation and the conventional classic setup of the distillation followed by the reaction followed by the distillation, your space occupation will be obviously less, because you are combining two unit operation into one. So the space occupation will be less, And the another thing is that okay, your whatever you do, the safety of the workers and the safety of the surrounding people should never be hampered. So yeah, because you are combining two setups into one, so sometimes it may be complex to handle such scenarios, such equipments. So yeah, you require very trained personnel so that safety is never hampered. And yeah, you need to also look out for the health and the society impact. So these are the three points of the triple P advantage that is addressed by the intensification for the distillation by reactive distillation process. So now let me discuss the reactive distillation column design. So as we have discussed what is the importance of the reactive distillation, now let us go and discuss what are the design aspects, what are the different designs that we can do for the reactive distillation column. So before going into that, one of the example is discussed in the lectures where the professor, the sir has discussed that okay, Eastman's first methyl acetate reactive distillation tower was started up in 1987. It contains 5 functions in one column, thus resulting in the capital expenditure and energy reductions by a factor of 5 relative to the conventional unit operation design. And so the Eastman's first methyl acetate reactive distillation tower was started up in 1987. So what was the reactive distillation tower was doing was it was basically to synthesize methyl acetate. It was set up in 1987 by the Eastman company. And so surprisingly, so it is not just that okay, it will combine only reaction and distillation, but it was able to incorporate 5 different functions into the one single unit operation. So which resulted not in just 20%. So we had just discussed that okay, it will be beneficial for 20% of the your energy and economy, but if you combine 5 functions into one, the resulting capital expenditure and energy reduction was up to the factor of 5, which is a lot. So yeah, reactive distillation column, if designed perfectly, if designed very carefully, you may get basically very high amounts of profit and optimization. So the column design requires relation in between. So for designing such columns where you want to basically employ more than combine 2 or more processes into one. So here the column design for the reaction distillation tower, you require the relation for the reaction kinetics with the performance chart or required performance, whatever you want. And similarly, you also need the relations for the mass transfer and heat transfer with the required performance. And you also need the relations between the impulse transfer to the required performance. Now coming to the stability of the equipment. Not the stability but the suitability of equipment. So what sorts of equipment are suitable, what sorts of material of construction are suitable for the basically construction or the setup of the reaction distillation tower, reaction distillation column. So we will discuss over it, and what are the various other combination and basically configuration that you can operate such a reaction distillation tower. So the suitability of equipment, basically, it depends upon two variables, that is reaction velocity, and it also depends upon the reaction volatility, and based upon that you will have different scenarios, and such as your concern may be to basically that okay, what is your suitability based upon your reaction velocity and the reaction volatility on the rectification column. And based upon that, so similarly, based upon depending upon those two variables, you will determine the column with larger volume in the bottom. So you may get result in that you may settle with that okay, you need a reaction column with larger volume in the bottom, basically to perform separation and to separate out the supernatant. And other than that, you also need to also verify that okay, either you need a stirred vessel with a rectifying column, or you need a stirred vessel with full column. And similarly, you may need a vessel cascade with column, or sometimes you may also need a stirred vessel with an evaporator, or simply an evaporator. So based upon your reaction velocity and reaction volatility, you may use certain equipments. So yeah. Now coming to the that was for the various based upon the reaction velocity and relative volatility. But what about if we try to classify in terms of the heterogeneous and homogeneous catalysis reaction? So let me first discuss about the reactive distillation, but in the case of homogeneous catalysis. So the homogeneous catalysis allows for the reaction velocity to be influenced by changing the catalyst concentration. So you can control one. So one way to control the homogeneous catalysis reaction is by controlling the catalyst concentration, and such catalyst concentration can be varied by basically changing the flow rates and changing the physical properties of the fluids. So yeah, we have discussed that okay, the three things in which upon which the flow regime depends upon is the geometry, channel geometry, and the fluid properties and the fluid flow rates. So here also similarly, if there is a homogeneous catalysis reaction, so your catalyst, your phase in which the catalyst is present may also be fluid. So may not may, but it will definitely be a fluid, and your reactants will also be consisting in that same phase because it is a homogeneous system. So here it might depend upon that okay, you need flow rates and you need to control the catalyst concentration in the fluid phase. Now the reaction velocity can be adapted over a wide range to meet the needs of the distillation equipment. So yeah, here by controlling the concentration of the reactants, you can control the reaction velocity and make it adapt to a wide range of the needs and requirements of the distillation equipment. Now that was all for the homogeneous catalysis system. Now suitability of the reactive distillation equipment for the heterogeneous catalysis reaction. So here the challenge comes that okay, here your catalyst particles are not necessarily in the same fluid phase, but rather it can be in solid phases. So here the challenge comes of the contact. So again, based upon your different reaction velocity and relative volatility, you may have a rectification column with the catalytic packings, or you may get a rectification column with catalytic internals and downcomers, or you may use a rectification column with side stream reactors. And similarly, you can also look out for that, okay, column and reactor system setup with a pump around, or you can also opt for evaporator and reactor with a pump around. So yeah, this is how you can perform the process intensification to intensify the distillation operation for the heterogeneous catalysis systems. The heterogeneous catalysis requires a structure to fix the catalytic particles in the reaction zone. So as compared to the homogeneous catalysis system, heterogeneous catalysis system will have a requirement of the catalyst as solid particles. Now one of the way is that you can suspend those solid particles, obviously to get a better contact into the liquid phase itself, but then comes that okay, you need to separate them. So yeah, that will be a challenge. So you need to then employ a different separator also for that, not just a distillation operation. You need a particular physical separator out of it to basically recover the suspended catalyst particles. Another way is that okay, you can basically create a structure, or a structure can be made where you can fix the catalytic particles in the reaction zone. So that is how you can carry out your heterogeneous catalysis reaction system. So, in those scenarios, what would happen is that your catalyst concentration will be limited upon the structure. So, whatever for an example, and just give an example. So, if your structure has because your structure will be fixed, your specific surface area, the net available specific surface area for the contact to happen will also be limited based upon the structure. So it will be limited. So no matter what you do, you cannot increase or decrease. So based upon it, so for example, if your demand has decreased, so if you do not want to use the catalyst, some amount of catalyst, so but no, you cannot do that. You cannot decrease your catalyst amount on command, because it is fixed to the structure. So yeah, so it will be limited. You cannot increase or decrease as per your wish. So that is one of the major limitations for that, such structure will limit the catalyst concentration. Now another issue is that the reaction velocity can be enhanced only to a certain limit, which will be set by the attainable concentration range. So because your catalyst concentration is set to a given limit, and it cannot be increased or decreased, so this is the reason why that your reaction velocity can also be enhanced to a particular limit only, where then again it will hit the wall, and that wall will be hit, and the reason for that will be that okay, your attainable catalyst concentration is on up to a certain limit only, up to a certain range. So you cannot further enhance beyond that wall. So the enhancing, so one way to enhance that reaction velocity is by utilizing higher temperature and pressure. But again, no, that is also limited if the catalyst consists of ion exchange particles. So yeah, that will again be limited, that okay, you cannot use a combined benefit of both catalyst and increased temperature and pressure to basically increase or decrease your required reaction velocity. If in such scenario, if in the case of the catalyst consisting of ion exchange particles, so in those scenarios, even increasing or decreasing the pressure to enhance the reaction velocity will not work. Now I wanted to discuss that the application of computational fluid dynamics. So how does the computational fluid dynamics will help into this scenarios? The computational fluid dynamics, the application of computational fluid dynamics programming, and in combination of the rigorous rate-based process simulation can be assessed. So performing those simulations can give you an idea which sort of suitable equipment is able to fit your suitability standard for the process intensification by combining both reaction and distillation system to get your reactive distillation setup. So you can perform CFD studies of your ideal or some proposed ideas, and then choose which one of them is the best. The three following tools can be used. So some of the three tools that basically combine the workflow of CFD in combination of the rigorous rate-based process simulation are Advisor. One of such software is Advisor, which is a software tool for internal pre-selection. And then another very popular software is the CFX Intent, which is a software tool for the fluid flow and reaction simulation. And then there is another tool called as Profiler, which is a rate-based flow simulator. So yeah, this is how you can combine the CFD workflow to perform process intensification, especially in case of the distillation, that okay, you can combine the fluid flow, the simulation of the fluid flow with the reactions, and see that okay, which one of the equipment perform best for your system, and then use that proposed idea to basically perform your process intensification. Now coming to what are some of the different types of reactive distillation process intensification. So to perform the next level process intensification, you would require more advanced reactive distillation configuration, which would allow an additional range of operating conditions, which is generally not available in the conventional classic reactive distillation setup. So that is why you can develop, or you can perform further process intensification. So yeah, because reactive distillation is a very old technology, but yeah, but quite successful. But you should not stop there. So yeah, people have then perform intensification furthermore for such reactive distillation setups to basically give birth to some novel reaction distillation setups, and we will be going through a few of them. But so few of those such novel reactive distillation setup that are born from the classic reactive distillation setup, when the process intensification is applied to it, include the reactive dividing wall columns and reactive cyclic distillation, which is also called as RCI-dist. And then another is the reactive heat integrated distillation column, which is called as RHIDIC, where the R is basically the reactive, and which is internally heat integrated. So this setup integrates the heat internally into the distillation column, to be more specific, the rectification chamber of the distillation column. Now another example is the reactive high G distillation. So we have discussed quite a lot on the high G distillation setups in previous in initial weeks, that okay, how the high G distillation tower used centrifugal force to perform distillation. So yeah, now what about if you can combine a reaction setup, reaction unit operation to the high G distillation system? So that would perform even better. So that is the idea of developing a novel reactive high G distillation tower, which is abbreviated as R high G. And then comes that okay, you can also to perform the separation task, why to just only limit yourself to the distillation, because distillation will operate upon the fluid solutions. Then you can basically, if you have particulate matter, so then you can basically combine your membrane separation with the reactive distillation setup. So here three different unit operations or three different tasks are combined. So the two of them are anyway separation. So you will perform separation via distillation, and you will also perform separation via membrane system. But then you are also combining the reactor system into the distillation tower and the membrane setup, membrane unit operation, or membrane separation unit operation. So basically you would get membrane assisted reactive distillation. So yeah, here you can combine, basically the idea remains the same, that okay, you can combine multiple different physical phenomena to basically perform a process intensification. So yeah. So another one is the microwave assisted reactive distillation. So again, in the previous few lectures we have seen that okay, how microwaves can be used to perform process intensification. Now even better if you can combine those microwaves in the reactive distillation setup, so that you can perform this separation via not only just distillation but also via microwave. So here the microwave will not enhance the separation, but microwave will enhance your reaction. So the reaction can basically get uniformly heated, or they get a uniform energy such that they can cross the energy barrier. So that is what is that okay, you will take microwave assisted reaction distillation to basically further enhance the reactive part of the reaction distillation. Another example is ultrasound assisted reactive distillation. So we will not look into it much, but our main focus will be on the reactive dividing wall columns, reactive cyclic distillation, and your reactive heat integrated distillation column, and reactive high G distillation, and membrane assisted reactive distillation. So these are the 5 reactive distillation setup that we will be going through in a very detailed fashion. Now starting with the reactive dividing wall columns. So yeah, so what is the idea behind reactive dividing wall columns? The dividing wall column, or the DWC technology, is expanding its use to azeotropic separation and reactive distillation. So that's where you can add the word R into the dividing wall column technology. So hence the reactive distillation performed in a dividing wall column is developed in academia and applied industry. And this application of the reactive distillation into a dividing wall column is what leads to the birth of reactive dividing wall columns. So the advantages that are demonstrated by this reactive dividing wall columns are reactive distillation, reactive dividing wall columns, which are highly integrated processes. So the advantage is that these highly integrated process will show is high conversion, increased selectivity and product purity, and significant energy and cost savings. So these are a few of the advantages for running the reactive dividing wall columns. Now, why to intensify the reactive dividing wall column? So why to do it? So because it has a very strong potential to improve production yield, to save 15 to 75% in the energy use, and over 20% in the capital cost as compared to the conventional processes. So that is why many researchers are looking towards that, okay, to perform the intensification of a reactive wall, reactive dividing wall columns, because it has a lot of potential and it has a very strong potential to improve the production yield. So yields can be improved up to about such that it will save about 15 to 75% of the energy usage and over about 20% in the capital costs as compared to the conventional processes. So that's a lot. So 20% savings is a lot of money. And yeah, 15 reduction in the usage of energy for about 15 to 75% is quite significant, I would say. That's a very, very big range. 15%, yeah, quite not a very big jump, but yeah, but appreciated. Now the another so why to perform the intensification of reactive dividing wall columns is that the limitations of the reactive dividing wall columns that relate to the catalyst formulation, hold up and residence time, and pressure drop and flooding is required, and the equal pressure is also required in a dividing wall column. So these are some of the factors that is holding back, but these are quite simple things. So if you can basically remove them or work towards them, so the intensification of our reactive distillation wall column can go up to 15 to 75% of the energy savings and 20% the capital savings. So now another point on why the intensification of a reactive dividing wall column is required. So because they are one of the main application are for the reversible reactions with suitable boiling point characteristics. So many of the distillation towers or reactive distillation tower, they do not have the capability, or they basically do not want to run for the or perform the application for reversible reaction. But here in this case, the reactive dividing wall column, if intensified further, can take on the challenges for the application of the reversible reaction with the suitable boiling point characteristics. Now, the few of the examples that are made using the reactive dividing wall technology is the methyl acetate, dimethyl ether, fatty acid methyl esters, biodiesel, and diethyl carbonate. Now, coming to the second type, so we have discussed about the first type, the reactive dividing wall column. Now, let us go to the second type, reactive cyclic distillation, or catalytic cyclic distillation. So basically CCD. So it has a catchy name. Instead of a reactive cyclic distillation, we can use catalytic cyclic distillation or CCD. Okay, so now we will discuss on catalytic cyclic distillation or reactive cyclic distillation, but yeah, CCD is a much better catchy name. So the catalyst cyclic distillation is yeah. So as per the case in 2013, so it is an innovative way of fluid separations due to intensified way of thinking in contacting the liquid and vapor phases. So here, unlike the conventional operation, the cyclic distillation uses a separate phase movement SPM technique that can be achieved with the technology specific internals and a periodic operation mode. So yeah, that's where your name cyclic comes into play. That unlike in the conventional operation, in this operation what you are going to do is basically you are performing separate phase movement and also you are using an periodic operation mode to basically run them in cycles to achieve a better selectivity and yield. So now there are two modes of operation for catalyst cyclic distillation. So what are those two operations? The first operation is a vapor flow period, and the second operation is a liquid flow period. So these are the two operations in which your catalyst cyclic reactor distillation tower can operate. So when a vapor flow period is used, this is where when your thrust of rising vapor prevents the liquid downflow. So this is how that you will blow up the vapor phase. And due to the vapor flow that is provided over a period, so this will thrust the rising vapor, and this thrust of the rising vapor is what will prevent the downflow of the liquid media. So another flow operation is the liquid flow period flow operation, where your liquid flows down through liquid flows down the column and dropping by gravity from one tray to another tray below. So yeah, in one operation your liquid is not allowed to fall down because of the thrust of the rising vapor, and in the second operation your liquid fluid will flow down the column via gravity from one tray to another tray. So adding a catalyst on the trays leads to the catalytic cyclic distillation, that is as novel process intensification approach in reactive separation. So here your trays will have catalyst, and the entire tower will be operated in a cyclic mode with periodic operation. Now on to that, why catalyst cyclic distillation is important. So the internals used for the cyclic distillation without and with solid catalyst on the tray. So it is not that you will operate the catalytic cyclic distillation tower only with the solid catalyst that are available on the trays. It can be operated with and without solid catalysts available on the tray. Now such a setup has the ability to control the amount of liquid on the tray and thus the reaction time. Now as the liquid holdup and the amount of catalyst per tray can be significantly greater than in the conventional reactive distillation system, so the applications to the slower reaction becomes feasible, thus extending the range of applicability of reactive distillation. So it will be applicable to the slower reactions too. So you can also perform slower reactions in catalytic cyclic distillation towers. So yeah. Now challenges and limitations of catalyst cyclic distillation. The key challenges are that include that there are moving parts, especially in the presence of catalyst particles. So yeah, and moving particles are generally moving parts are prone to damage. So you need to keep in check in what is the available flow rate, what is the range of flow rate where those moving parts can be able to handle. So you need to run the reactive distillation tower, catalyst cyclic distillation tower, for that conditions only, if you do not want to harm your moving parts. And another challenge is the obtaining of a good mixing. So yeah, mixing is anyways a very big issue in entire of the chemical industry. So actually the whole the chemical engineering, the heart of the chemical engineering lies in the mixing. How well can you mix? So that is the idea. Now coming to that, okay, you can also include turbulence. So the turbulence in the liquid phase for enhancing the reaction can be included, but employing such turbulent flow can potentially damage the catalyst particles. And yeah, again, as I have told that, okay, because it involves the employment of the moving parts, so it can damage that also. So you need to take care that, okay, in what sort of flow rates are you operating, such that it does not go beyond what are the prescribed flow rates for operating the equipment is. And especially because the turbulence can enhance the reaction, they can enhance the process, but the turbulence can also cause damage to the catalyst particles that has been fixed to the system chassis, and also it can also damage to the moving parts. Now, adding structured catalytic packing or catalytic internals on the tray may overcome this challenge. So that is one way that, okay, you can add the structured catalytic packing or catalytic internals on the tray to overcome this sort of challenge. Just as with the reactive distillation technology, the catalyst cyclic distillation is limited to liquid phase reaction, for example, to relatively low temperatures and for slow reactions. Now coming to the advantages of the catalyst cyclic distillation, this cyclic mode of operation, so the crux here, or the main thing that makes it special, is the operation in cyclic mode with periodic condition. So this cyclic mode of operation leads to the key advantages compared to the conventional trade columns: high throughput and equipment productivity, high separation efficiencies, about 140 to about 200% of the Murphy efficiency, reduced energy requirements, about 20 to 35% of the savings, and increased quality of the products. So now let us go to the next example of the applied process intensification to the reactive distillation setup to get a better. So another such example is the reactive heat integrated distillation column, or HIDIC. So what is the idea behind reactive heat integrated distillation column, if you may ask? The idea is that, okay, it is a heat pump assisted distillation which uses internal heat integration So the whole rectifying section of a column is the heat source, while the stripping part acts as a heat sink. So this setup uses the heat that has been generated by the rectifying section as the heat source and integrates that same heat to the stripping section, which acts as a heat sink. So yeah, you are basically utilizing cleverly the heat generated. So instead of making that heat go to waste, you are integrated that internal heat to perform your operation or to assist your operation via heat pumps. So the heat is transferred from the rectifying section, which is usually operated at very high pressures, to the stripping section. Now the combining of the HIDIC, or basically heat integrated distillation column, with reactive distillation systems in a single unit leads to a reactive system, which is called as basically reactive HIDIC or RHIDIC, with potential for industrial application. So why not combine the reactive distillation with the heat integrated distillation column, so that you will get reactive heat integrated distillation column, RHIDIC. So the RHIDIC has the potential to be applied to azeotrope forming mixture, as a reaction can consume the azeotropes. So for example, like tert-amyl methyl ether production and ethyl acetate synthesis from acetic acid. If you may ask, what are the advantages of HIDIC? The heat required for the evaporation in the stripping section is obtained from the rectifying section, thus reducing the heat duty of the reboiler. So the reboiler heat duty is reduced since the reboiler is assisted by the heat that has been obtained from the rectifying section to provide the heat of evaporation to the stripping section. So your duty of the reboiler will be reduced. So this leads to the energy savings, and if you so the numbers here are quite large, that okay, the primary energy savings can go from about 70, can range up to 70 to 90%. So that's a huge energy savings. So the reactive heat integrated basically RHIDIC resulted in 22% of saving as compared to your classic reactive distillation setup. So even the reactive distillation setup can give you benefits. So this in particular, so basically performing intensification operation further along, you can get with RHIDIC about 22% of the savings overall. So industrial installation would require, or the industrial installation implementation of HIDIC, or which is also called as the super HIDIC by there is one company which has done that is Toyo Engineering Corporation, Japan, where they have industrially installed the super HIDIC. Now, what is the disadvantage of HIDIC? So the disadvantage of HIDIC is the range of applicability. So it has very quite narrow range. So the range of applicability, which is basically the how it is beneficial to equilibrium limited reaction, is likely to be narrower than that of the conventional reactive distillation column. For example, like close boiling mixtures, that is basically to avoid high pressure ratio in rectifying and stripping section, because if there will be high pressure ratios among those two, so the heat that is released from the rectifying section may not be beneficial for the stripping section, because that heat which may be coming from a very low pressure zone, so yeah, will not be of sufficient quantity. Now let us go. Okay, so yeah, this is the reactive heat integrated distillation column. Now let me discuss on the another example, which is the membrane assisted reactive distillation. So the membrane assisted reactive distillation, or MARD, is basically, you are combining membrane separation with reactive distillation. So yeah, it is a hybrid operation. So hybrid separation processes such as the distillation and the membrane separation can be combined to basically, you are basically combining here two or more unit operation which will contribute to a given separation task by means of different physical phenomena. So membrane is where you are utilizing different, the physical phenomena. What you are using is basically the difference between the size, and in terms of distillation, what you are using is basically the difference in terms of the boiling point. So yeah, you are combining two different separation tasks which is governed by two different physical phenomena into one to intensify the process overall. So here you are combining the reactive distillation, where the separation task is the distillation, and you are incorporating another task on top of it, that which is membrane separation task, to basically get membrane assisted reactive distillation. Now they are integrated such that the synergistic effect allowed to overcome the limitations of the individual unit operations. Mhm. So membrane assisted distillation processes constitute one possible type of a hybrid separation process. Now, what is the principle of membrane separation? So the principle of membrane separation, so we will discuss on it. So in membrane separation, a feed mixture flows over a membrane which allows for some molecules to pass the membrane while others are rejected. So the flowing particles which are passing the membrane are passing through the membranes are called as the permeate, while the rejected stream is called as the retentate. The mass transfer is based on different physicochemical interactions between the components with the membrane. So yeah, so the governing mass transfer, so the basic terminology is that okay, whatever passes through the membrane will be called as permeate, and what will be rejected will be called as the retentate. And the governing mass transfer phenomena over this operation is basically based on different physicochemical interaction that happening between the components, species components with the membrane. So what are the advantages of MARD? The advantages of MARD include that the membrane assisted distillation will integrate the advantages of distillation, and specifically its robustness and high capacity with the advantages of the membrane separation. So you get the benefits of both the process, the benefits of and advantages of distillation with the advantage of membrane separations. And they can also be used for the flexible capacity. They can also be used for flexible capacity as that increases due to their modular nature, and they can easily be scaled up and integrated into the existing processes. Now, what are the different configurations for MARD? So there are four different configurations of MARD. The configuration A, the feed mixture is separated until the occurrence of a separation boundary happens. So for example, in a low boiling azeotrope which will exit as a distillate. Then the configuration B, it consists of a membrane at the bottom if a homogeneous catalyst containing some reactant needs to be recycled into a reactive distillation via retentate recycle. And the configuration C, it represents the high selectivity of the membrane that is used to pre-fractionate the mixture, which relieves the distillation column, and this process may lead to smaller distillation column and lower reflux ratios. In the configuration D, the membrane is used to separate a three-component mixture. So these are the advantages of MARDR, that okay, you can use its modular nature. So now we will discuss what are the advantages of MARDR. So there are very number of advantages. So we will go over them one by one. The advantages of MARD are that membrane-assisted distillation offers significant potential for the separation of close boiling or azeotropic mixtures. So yeah, because here you are also involving the membrane, so it assists in the separation for the close boiling or azeotropic mixtures. Now, in contrast to the distillation, the membrane separation is not limited by the vapor-liquid equilibrium and can thus overcome azeotropes and distillation boundaries. So, this is one of the biggest advantages, that you can perform azeotropic separation by distillation of the azeotropic mixture by basically combining the membrane separation and the distillation process both. Now, another advantage is several advantages are that high selectivity, low energy consumption, and a compact and modular design are further advantages of membrane separation. So you can combine the modular advantages of the membrane separation into the MARD, membrane assisted reactive distillation. So here you would get high selectivity, you would also get low energy consumption, and a compact and modular design. Membrane processes are not usually economical. They are quite hefty, they come with a very hefty price, they are not very economical. So why they are not economically viable? Because if large permeate flow rate or large purities of the both permeate and retentate streams are required, then they become very non-economical, because in such cases membrane separations are not usually robust, and they do not handle they do not fare well with large quantities. So that is why if the requirement is of very large permeate flow rate and very high purity of both permeate and retentate are required, so then your membrane processes will not be economically viable as compared to the other processes. But yeah, they do have their own advantages. And membrane assisted distillation combines the advantages of both separation principle, and it operates without an additional separation agent. So but the advantages are that here you do not need an additional separation agent, so that is why it can result in a reduced energy demand, emissions, and investment cost. Now, what are the disadvantages? So before going to further disadvantage is basically that it is not economically viable. Now going to the application part of it. So in terms of application, the use of evaporation of PV to break the low boiling methanol methyl acetate azeotrope during the transesterification of methyl acetate with butanol. So it's a paper by Steinweg and Melling in 2004. So another paper by von Scala and other people in 2005, that this integrated process has also been applied to the production of cosmetic fatty acid esters. So the production of cosmetic fatty acid esters has been utilizing the principles of MARD. So, but especially in the per evaporation, the feed is introduced into the membrane in the liquid state, and the retain rate remains in a liquid while the permeate is vaporized. So yeah, here is where you will use distillation to basically evaporate the permeate or vaporize the permeate. Now let me briefly discuss on the reactive high gravity distillation or high G distillation. So as we have discussed that high gravity technology or high G technology replaces the usual gravitational field by a centrifugal field achieved in a specially shaped rotating device. So the high gravity field about 100 to 1000 Gs shift the flooding limit and allows the use for the dense packing material with a high interfacial area. Now, what are the advantages of high G? The HETP values in the high G are as low as about 2 to 8 centimeters. So, yeah, that is quite a very advantageous value. And the volume reduction of a factor of 4 to 7 for certain distillations as compared to classic columns. Now, adding a catalyst to convert the system into a reactive high G distillation is very possible. Now, the solid catalyst in the wire mesh packing allows for the potential of high G for solid catalyzed gas liquid reaction and even for reactive distillation. Now, as early as in 1999, the Dow Chemical successfully introduced one of the first chemical applications of reactive packed beds, namely the reactive stripping of hypochlorous acid. Now, what are the shortcomings of the high G? So, the shortcomings of the high G include operation at high gravity may result in erosion of the catalyst, which are entrapped in the internals, for example, like a wire mesh, where very low liquid holdup and correspondingly low residence times that may limit the application to the reactive system with very high reaction rates. Therefore, the reactive high G technologies need more research to enhance packing design and its hydrodynamics. The range of applicability is limited to liquid phase reactions only and includes fast reaction with competing serial reaction to achieve enhanced selectivity and ensure low yield losses. Now, comparison of if we would discuss the comparison of different reactive distillation processes with other process intensification technology, we see that in terms of energy savings range, the conventional reactive distillation technology will give you about 15 to 80% only, and if you would combine the reactive distillation with the wall columns, there you would get about 15 to 75% of increment. And if in the cyclic catalytic cyclic distillation, you would get about an energy savings of about 20 to 35%. And in our HIDIC systems, you would get about 50 to 90% of energy savings range as compared to classic processes. And in terms of reactive distillation combined with high G distillation, you would get about so it has not been recorded, but yeah, there will be no energy savings. Now, coming to the microwave assisted reactive distillation, or MWART. The microwave assisted reactive distillation can be an useful alternative to the use of the alternative energy forms in industrial esterification. Now, what are the advantages of microwave heating? The advantages of microwave heating that we have also discussed previously are selective energy absorption, non-pollution, and high energy efficiency and high product quality. Now, what is the mechanism of the micro-assisted reactive distillation? So, when a microwave field is applied, a dielectric heating takes place that differs in the mechanism from the conventional heating. Now, during the conventional heating, the highest temperatures that can be reached are at the surface of a vessel where the bubbles can form and thus boiling occurs. But in contrast to that, the dielectric heating gives rise to an inverted temperature gradient because of the volumetric heating, where the energy is dissipated over the entire volume. The dielectric heating is mainly affected by the two mechanisms: dipolar polarization and ionic conduction. Now, in the dipolar polarization, the heating is induced by molecular friction due to the rotational motion of polar molecules induced by the electric component of the microwave field. And in the ionic conduction, the ionic bonding of many refractory compounds such as the carbides and nitrides allows for the ionic diffusion and correspondingly under the influence of an electric field. So the microirradiation can lead to an accelerated separation of one or multiple components via vaporization in the reaction system to overcome the equilibrium limitation to impel the reaction in the desired direction. For example, an industrially relevant demethylation reaction by microwave can prove the effect of breaking the equilibrium constant through the elimination of gaseous byproducts such as methyl bromide by microwave heating. So now advantages of MWARD or microwave assisted reactive distillation. So by means of microwave irradiation into the reactive distillation column, the reaction rate for a slow reaction can be enhanced. So if a reaction is particularly limited, thermally limited, so by means of microwave irradiation into the reactive distillation column, the reaction rate for a slow reaction can be enhanced. Because generally for other heating systems, the other heating systems are surface limited, but here the microwave is basically your it is volumetric heat generation. So yeah, the efficiency of distillation separation can be improved. The irreversibility associated with the distillation separation operation can be reduced by bulk heating of the microwave irradiation. Now, other advantages are that the reaction section and the separation stages would be reduced by improving the reaction rate and separation efficiency, because there is an overall improvement in the reaction rate and the separation efficiency, so it would lead to the reduction in the section size of this reaction and separation stages. A smaller column and the reflux ratio can achieve a specified separation. Now, the improvement in the system performance can permit the further reduction in capital investment and therefore leads to a more compact process design, which is one of the main features of the process intensification. So this is because of the smaller columns and reflux ratio can achieve a specified separation. For achieving a specified separation percentage or separation efficiency, you would require much smaller column and much lower reflux ratios, and thus you would get an overall improvement in the system performance, which would allow you to further reduce capital investment and therefore lead to a compact process design, which is one of the main features of process intensification. Now, furthermore, recent research results indicate that the microwave irradiation may affect the separation of mixtures, which would lead to a more efficient distillation processes. Microwaves might enhance the concentration of low boiling components in vapor, as per the Altman and others in 2010, and also influence the position of an azeotrope in terms of temperature and composition. So yeah, this will be all for this week. If you have any doubt for the course content of the next week, you can feel free to come and ask. Otherwise, if not, I will be just briefly discussing what has been discussed in this week, in the tomorrow's week. So anyways,